dear children, welcome to digital class. How are you children? Hope you are doing fine. In our previous class, we discussed about refraction of the light at plane surfaces, regarding the definition of the refraction, how the light behaves when it travels from one medium to another medium, and refractive index, measurement of the refractive index using a semicircular glass slab. Today, we are going to take some other topics related to this same topic. Children, we begin our lesson with a small activity, how the light behaves when it travels from denser medium to rarer medium. In our previous lesson, we discussed about how the light behaves when it travels from rarer medium to denser medium. So, for this activity, let us see what is taking place here. This is a metal disc. We are taking a metal disc. That metal disc is now divided into 4 parts along the line mm and perpendicular to mm. Along the mm line, we can take 90 degrees, and along the vertical line we can take 0 degrees. The metal disc is now divided into 4 parts, mm and perpendicular to mm. Now, what we have done to this metal disc? The circular metal disc is attached with 2 straws. So, we are taking 2 straws here. The 2 straws are fixed at the midpoint of the metal disc. One straw is in the air, other straw is in the water. The 2 straws can rotate freely such that there is not having any disturbance. The first straw, which is kept inside the water, is making an angle 10 degrees with the normal. The second straw is in air. We have to see through the second straw such that the water can be seen through the second straw. We have to adjust the second straw such that the water will be seen through the second straw. Once we see the water through the second straw, take out the metal disc. When you take out the metal disc from the water, it looks in a curved path. Why it is in curved path? Because when light travels from denser medium to rarer medium, the direction of the light ray changes. This phenomena is said to be also as refraction of the light. Children, can you find any relation between this angle of incidence and angle of refraction by any mathematical relation? Yes, we have one mathematical relation which gives about the relation between angle of incidence and angle of refraction, which is called as the Snell's law. The Snell's law states that the relation between angle of incidence I and angle of refraction R can be given by n1 sin I is equals to n2 sin R. This n1 sin I is equals to n2 sin R, it is a mathematical relation which gives about relation between the refractive indices of the pair of medium and angle of incidence and angle of refraction. Here n1 is taken as the refractive index on the incident side. We are taking the incident side as a first medium and refracted side is taken as the second medium. The first medium refractive index is n1, second medium refractive index is n2. Now, we modified the relation as sin I by sin R is equals to n2 by n1. We know that n2 by n1 is equals to V1 by V2 from the definition of the refractive index. Already we discussed about refractive index in our earlier class. The refractive index of any medium is inversely proportional to velocity of light in that medium. So, based on that relation, n2 by n1 is equals to V1 by V2. Therefore, the equation sin I by sin R becomes V1 by V2. Then when light travels from one medium to another, the ratio of speeds is V 1 by V 2 and the ratio of refractive indices is N 2 by N 1. Now, angle of incidence and angle of refraction will follow sin I by sin r is equals to ratio of the velocities V 1 by V 2. Children, we will going to learn some interesting principles regarding this refraction of light. Children, see this image carefully. What you are seeing here is you are seeing a diamond. How the diamond looks like here? It is shining very brightly. Do you know what is the reason for the shining of the diamond? Children, see this image. In this image, what do you observe? Yes, we are seeing shining water drops. Do you know what is the reason behind these two images? Why the diamond is shining brightly? Why the drops are looks very shiny? To know the reasons behind this particular phenomena, we have to learn about critical angle and also total internal reflection. Children, see here in this image we are seeing that light is moving from denser medium to rarer medium. The denser medium here water and rarer medium is air. As the light is travelling from denser medium to rarer medium, the refracted ray should bend away from the normal. Suppose if we go on increase the angle of incidence at a particular angle of incidence theta c, the refracted ray is grazing along the surface. When the refracted ray is grazing along the surface, we treat that angle of refraction here is 90 degrees. That means, as the angle of incidence increases, the refracted ray bending away from normal, but for a particular angle of incidence, the refracted ray is moving along the surface. Is there any name for this angle of incidence? That is nothing but critical angle. Critical angle is defined as when light ray travel from denser medium to rarer medium, the angle of incidence in denser medium for which the angle of refraction in rarer medium is 90 degrees is called critical angle. So, when the light ray travel from denser to rarer medium, the angle of incidence in the denser medium for which the angle of refraction is 90 degrees, it is said to be the critical angle. See here. So, this is the image related to the critical angle, light moving from denser to rarer medium. Again theta c is the critical angle, angle of refraction is shown here as the perpendicular, that is 90 degrees. Now, we will discuss about is there any relation between the refractive index and the critical angle of the given pair of medium. By using Snell's law, n 1 sin I is equals to n 2 sin r. Here refractive index of denser medium is n 1, refractive index of rarer medium is n 2. If the angle of incidence I is equals to c, called critical angle, angle of refraction is 90 degrees. Now, substitute the values here. In the place of I am substituting c, in the place of r we are taking 90 degrees. That implies n 1 sin c is equals to n 2, because sin 90 degrees is equals to 1. This we can learn in mathematics. Therefore, n 1 by n 2 is equals to, we can write 1 by sin c, or n 2 by n 1 is equals to sin c. Here n 2 is the refractive index of second medium, n 1 is the refractive index of the first medium. Always we can consider that n 2, the second medium, is the medium where the refraction of light take place, n 1 where the medium the incident light is present. incident medium is first medium and refracted side medium is the second medium. Suppose if air is the rarer medium in any condition, then N2 must be taken as 1, because refractive index of air is equals to 1. Then the relation has modified as 1 by N1 is equals to sin C. Finally, we can write N1 is equals to 1 by sin C. This is the relation between the refractive index of the medium and critical angle for a particular medium if it is moving from any denser medium into air. If it is only air, then only we can write N2 is equals to 1. We are taking N1 is said to be the absolute refractive index of the first medium. The absolute refractive index of the first medium is equals to 1 by sin C. Always the refractive index is inversely proportional to critical angle. If the refractive index of any medium is very high, the critical angle in that medium is very less. Let us see a small numerical based on the relation between refractive index and critical angle. See this numerical. Children, determine the refractive index of benzene if the critical angle of benzene with respect to air is 42 degrees. See here, we are finding the refractive index of the benzene, and given that with respect to air means the refractive index of air is equals to 1, then only we can apply n is equals to 1 by sin C formula. N is equals to 1 by sin C formula applicable only if the second medium is the air. Now, given here critical angle for the benzene in combination with air is 42 degrees. Let us take n is equals to 1 by sin C. In the place of C, substitute 42 degrees. Sin 42 degrees is equals to 0.67. Now, n is equals to 1 by 0.67, that becomes refractive index of the benzene with respect to water is 1.5. That means, by knowing the critical angle, we can find the refractive index, or sometimes if you given the refractive index, you can also calculate the critical angle. This n is equals to 1.5, it is also said to be absolute refractive index of the benzene. Children, we see that if the light travelling from denser medium to rarer medium, if angle of incidence is critical angle, then angle of refraction is 90 degrees. What happens if we go on increase the angle of incidence in the denser medium? See here, again we can take an example of the light travelling from water to air. Incident ray angle theta 1, refracted ray angle theta 2. Here the angle of incidence is less than the critical angle, therefore, the refracted ray is moving in the rarer medium. See here, we can see both incident ray in the denser medium and refracted ray in the rarer medium, and I increase the angle of incidence beyond the theta 1 and make up to theta c, the refracted ray is not in the air, it is along the surface of the water. This angle of refraction is 90 degrees and this angle is called critical angle. Suppose if we go on increase the angle beyond theta c, what should we observe? The incident ray and the reflected ray will be in the same medium. Instead of the refraction, the light again comes back into the same medium. This phenomena of reflection of the light again into the denser medium is called total internal reflection. So, to get the total internal reflection, what is the condition? The condition for the total internal reflection is light has to travel from denser medium to rarer medium. Its direction is towards the rarer medium only, but once incident on the boundary between the water and air, it again comes back. This property is called total internal reflection. Is the total internal reflection takes place for all angles of incidence? No, only the angles of incidence should be greater than the critical angle. Here theta 1 is more than this theta c angle. Therefore, again the light comes back into the same medium. According to the laws of reflection, these angles must be also equal, theta 1 should be equal to theta 2. From the laws of reflection, we learn in our 8th class, this angle of incidence is equal to angle of reflection. See the definition of the total internal reflection. When the angle of incidence is greater than critical angle, the light ray gets reflected into the denser medium at the interface. What is meant by interface? Interface is nothing but the boundary between the water and air. This phenomena is called total internal reflection. See here, for angle of incidence C, the red color light is showing that the incident ray is at an angle of critical angle. The refracted ray, the red color ray is the grazing along the surface, angle of refraction is 90 degrees. If we increase the angle, it again comes back. This is the diagram representing the total internal reflection. Children, can you give reason for the shining of the diamond and the water drops now? Yes. The reason behind the two above situations is the total internal reflection. When light enters into diamond, it undergoes multiple reflections, therefore, it appears very shiny. The same reason applicable for the shining of the water drops. Therefore, the total internal reflection have so many applications are there. We will see some more applications regarding this total internal reflection. Now, see what is mirages. In the picture, you can happen to see that a person is viewing a long distance tall tree. When he is observing towards, when he is watching the tree appears to him in the inverted position. This is due to one of the property of the total internal reflection. Why the person is seeing the tree in the inverted position? This is one of the optical illusion. Mirage is an optical illusion due to total internal reflection of light rays in the atmosphere. So, we see the total internal reflection not only between the light ray coming from water to air, it is also taking place in our atmosphere. This atmospheric total internal reflections leads to the mirages. During daytime, the temperature of the air in contact with the sand increases. We know that the land heats quickly. When sunlight falls on the land becomes heated. Once the land becomes heated, the air which is present on the land also heated. When temperature of the air increases, its density decreases. That means, when we move away from the land, the refractive index is increasing. When temperature falls, the refractive index will increase. Therefore, the light rays coming from the branches of this tree appears to be bent at a particular place. That means, up to here the light ray is in the downward direction only, but beyond this point the light is moving in the upward direction. That means, at this point the light is undergoing the total internal reflection, where the angle of incidence beyond the critical angle between the two particular places. Therefore, the person will see the image in the inverted position. Already we seen here, due to this difference in the refractive index, an optical illusion of the water in desert is created. We may have seen that on the highways, when you are traveling, you may see some water laying down on the road. That is because also due to optical illusion. We are seeing the road through a vehicle. We are traveling in a vehicle and we are seeing our main road. So, here this particular region appears to be having some wetness. The wetness gives us a feeling that it is having water, but when you travel up to here, we cannot find any water there. Why? What happened to that water? Actually, is the water present there? No, there is no water. That is also the optical illusion. This appearance of the wetness on the road, it is because of the refraction of the light in various layers of the air, and also this particular wetness is also image of the sky. When you go to this place, the wetness also move away from you. Another total internal reflection application we can discuss here. That application will have a wide role in our present day telecommunications. That is nothing but optical fibers. The optical fibers also working under the principle of the total internal reflection. Optical fiber is a transmission medium, carry the light signal without any appreciable loss. See here, we are taking a light pipe. Through this light pipe, we are seeing a number of optical fibers. This is the each fiber, through each fiber the light is coming out. This is the appearance of the light passing through each cable. An optical fiber is a very thin fiber made of glass or plastic, because glass or plastic can allow the light easily to through them. Transmission medium, also it is treated as a transparent medium. An optical fiber is a transparent medium also, which carry the light signal. An optical fiber is very thin fiber made of glass or plastic, having radius about a micrometer. Micrometer means 1 by 10 lakhs of a meter. It is very small dimension. A bunch of such thin fibers form a light pipe. So, in a number of optical fibers are formed in a bunch, and this bunch is connected to the transmitting station, and from that the light allowed to pass through it and reaches the receiver end. Children, so far we discussed about how the light ray behaves when travel from denser medium to rarer medium, and also principles like total internal reflection, critical angle, and other applications of the total internal reflection. Now, in our coming topic, we have to discuss about how the light ray is traveling when passes through a rectangular glass slab. With that activity, we are going to know what is meant by the lateral shift and vertical shift. Ray tracking of a glass slab and lateral shift. A thin glass slab is formed when a medium is isolated from its surroundings by two plane surfaces parallel to each other. Children, we will see an activity here. So, to discuss about vertical shift and lateral shift, I am taking an activity here. We have taken a white chart, keep a rectangular glass slab over the paper and give the outlines for the rectangular slab. Remove the slab, name the vertices A, B, C and D. Take a point at a convenient place on the AB line. Using a protractor, draw a perpendicular line for that particular point. Now, join these 2 points. It becomes the normal for the surface AB. We are naming the normal as N1, N2. And try to draw another line making an angle 30 degrees with respect to the normal. Put a dot there. Join the point on AB to that new point at an angle 30 degrees. This line becomes the incident ray for the given glass slab. We are keeping 2 pins. Now, keep the glass slab in that particular outline region. Now, we are able to see the 2 pins to the other side of the glass slab. Now, I am moving to a convenient position such that the two pins appear to be in a straight line from a position. Now, I am able to see the two pins in the same line. By seeing through the glass slab, insert one more pin in the same line as the two pins are there. See children, the third pin also appears to be in the same line. Behind that, we are keeping one more pin such that the four pins appear to be in the same straight line when we see through the glass slab. We are removing the pins and put the dots circles over that impressions of the pins. We can able to see the impressions of the pins that we can kept on the other side of the glass slab. Now, these impressions and the pins are not appear to be the same line now. When we see through glass slab, they appear in the same direction, but they are not exactly the same line when you see from the other side. Join these two impressions such that it meets the line CD. So, we are not marked there 30° angle. Extend the incident ray to passes through the CD line also. See here, there is a width between the two rays. That width is called lateral shift. That lateral shift we can take it as the x. Measure the distance between them, it is 2 centimeters. Again you can see the angle. I am drawing the normal. See the angle of emergence with the help of a protractor. The angle of emergence also 30°. See here, if we extend the incident ray, it is not meeting the emergent ray. Children, we have seen a video now. Now, see how the image looks like in a picture. See, it is the incident ray. Here we can take the two dots. The two dots indicate the two pins, the light incidenting on the first surface. It undergoes refraction and again emerges out of the glass slab. This is the original incident ray. The original incident ray and emergent ray having some separation. This separation is called as the lateral shift. The lateral shift is nothing but distance between the incident ray and emergent ray. On what factors the lateral shift is going to be depend? When you change the thickness of the glass slab, again the lateral shift will be changes with same angle of incidence. If you want to find out the lateral shift for different rectangular glass slabs of different thickness, then the lateral shift also changes. Second point is the lateral shift is also depend upon the angle of incidence. We can see a table here. For angle of incidence 30°, lateral shift is 2 centimeter, angle of incidence 45°, the lateral shift is 2.8 centimeter. For angle of incidence 60°, the lateral shift is 3.6 centimeters. So, that is we observe that the lateral shift depends upon the thickness of the given slab and also angle of the incidence. When angle of incidence changes, automatically the lateral shift is going to be change. Next we can discuss about the vertical shift. In this vertical shift, we have taken a glass slab, rectangular glass slab kept on the paper, keep a pin in the horizontal position at some convenient distance. Now, we are looking that horizontal pin through the other side of the glass slab at its edge. Try to coincide these two pins. Now, once the two pins appears to be coincide, if you remove the glass slab, there is some vertical separation between the two pins. See here in the diagram also we observed that original pin is above and the new pin is below, but when you see to the edge of the glass slab, the both pins appear to be in the same line. The distance between the real position of the object to this apparent position is called as the vertical shift. With respect to vertical shift, we can find out the refractive index of the material of the glass slab, which can be determined by using the activity of the vertical shift. Refractive index material of the rectangular glass slab can be determined by using activity of vertical shift. Refractive index is equals to thickness of slab by thickness of slab minus vertical shift. So, this is a formula to calculate the refractive index of the given rectangular glass slab. These are the keywords we learn in this particular topic: critical angle, total internal reflection, mirages, optical fiber, lateral shift and vertical shift. Improve your learning. The absolute refractive index of water is 4/3. What is its critical angle? What are the conditions for total internal reflection of light? Why do stars appear twinkling? Explain the formation of images. Explain the formation of mirages. Explain the refraction of light through a glass slab with a neat diagram. Children, hope you understand the concept clearly. In the next class, we can come with another topic. Thank you.